So today I'll be speaking about an embedding is worth 1,000 words. So how you can get started using word embeddings in your business. So a little bit about me. I know I just got the intro. I love math. I couldn't get enough of it. I was working on my third master's when I was like, no, I need to get a job. This is ridiculous. But I spent about a decade as a research scientist working for the DoD, primarily on military applications, images, video. This was before data science sort of hit the industry and everyone had lots of data to work with. After leaving the DoD, I moved to Austin, Texas, and I worked at a startup as a data scientist, primarily natural language processing and unsupervised learning. That's where I met Reagan, and that's how I got invited to this talk, because we work together. And then currently I'm a data science manager at HomeAway, which is an Expedia company. And I am the founder of the Women in Data Science Meetup group in Austin. And if you want to follow me on Twitter, I am Data Nerd Jaya, and I only post nerdy articles, no politics, no religion. So feel free to follow me. So I wanted to just get a sense of who is in the audience, because I know the list looked very diverse. So how many of you have a lot of unstructured text right now that you're in your company? Okay. And how many of you are currently doing something with that text using R, Python? Okay, some of you. Okay. How many are software developers in here? We've got a couple. Okay, data scientists, data analysts, students. Great. Okay. I've been given a lot of feedback, how technical, how not technical, so I will be skipping over a lot of my slides. I will be taking up the whole time, the whole 40 minutes, because I have a lot of material, but the slides will be available afterwards, so no worries. Let's start with a pop quiz. Nothing like a 10:30 in the morning pop quiz. So what is an embedding and why do I care? Is an embedding really worth 1,000 words? What does it mean for words to be related? What are some gotchas in dealing with text data? And what approaches can I use to get insights from my text data? Now you're in luck, we're not going to answer those right now. We'll answer them at the end. Just keep those in mind as we go through this talk. So I have to just say this up front. There are many parts of this talk that are very, they should be given a lot more time than I can give here in the 30 to 40 minutes that we have. So I will have to gloss over it, and I apologize. If you want to go more in depth, I would love to talk about this. I'm here till tomorrow night. Find me anytime and we can discuss more. And because of interest of time, I will not be including any equations. So for those who really wanted equations, again, find me afterwards and we can go through a lot of papers together and discuss whatever you'd like. So word embeddings. This term was actually coined recently, 2003, not that long ago. Before it was called word vectors. So if you've seen things in the literature, vectors, vector space model, word vectors, this is the same content as a word embedding. It's just now we're calling them word embeddings. Essentially, a word embedding is taking your text and converting it into numbers. We can't just throw text at a computer. We need to give it numbers. So the process of converting text into numbers is what word embeddings are in their essence. So they're actually not just for words. You can have sentence embeddings, you can have document embeddings. And this is not magic. I feel like a lot of times as a data scientist, people are like, oh yeah, just like throw it in the computer and cool stuff comes out. And it's like, no, there's a lot of work. There's a lot of work that goes into it. And so I want to really highlight that it's not magic. So why am I here? I think word embeddings are really cool. I've been using it for about 5 years now, seeing its evolution from the vector space model to some of the word-to-vec stuff. So I think they're cool. I wanted to show that there isn't magic. There is hard work. There is paying attention to your data. And the two things I really wanted to highlight in terms of the Python packages are GenSim and scikit-learn. So if you are using Python, I would highly recommend these two packages as a way to get started. All of the code and examples that I'll have at the end will be based on primarily GenSim. So if you're just looking for one thing to take away, use GenSim, get started on your data. There's so many built-in functionality in that package. It's a really great way to start. And that's what it looks like, so you'll know that you found the right, GenSim in scikit-learn. So what can we do with our text data? We can get insights, we can do search, retrieval. There's so much text out there, you're looking for stuff. We can cluster, we can find groups, we can find topics and themes. The really cool thing about word embeddings and all of the stuff I'll be talking about today is that you can actually apply this to other types of data. So if you have a bunch of images, so at HomeAway, we have vacation rentals, and people are looking at a bunch of vacation rentals. We can actually use, let's say, the images for those vacation rentals and apply the same techniques that we do to text. So anytime you have a collection of things, you can have click-through rates, you can have images, you can apply these techniques to make embeddings, to make predictions. Now, we're not going to be talking about predictions here. We're going to be talking about mostly unsupervised, like learning from the data. But find me afterwards if you want to talk more about that. So quickly, I'm going to gloss over this because I think most of you probably know these definitions. A vector, go back to, I guess, high school math. Just want to make sure everyone's see. So that's like the way vectors are represented. Clustering. So clustering is basically grouping points that are close. And when you're thinking about clustering, you should really think about, well, what does it mean for stuff to be close? Like, oh yeah, sure, yeah, if it's close, put them in the same cluster. But what is close? So this is a big list, and I have all the resources, again, for this. I just wanted to highlight that for text, there are many ways to define closeness. And so you can see here there's a bunch of character-based closeness. The two that are circled in red, cosine and Euclidean, those are the two that are shown here in this chart. So if you see this graph, you have points A and B. The Euclidean distance would be that line between them, labeled D, and the cosine distance is the angle between the two. Now I highlight those two because cosine similarity is what's happening under the cover in GenSim, and Euclidean distance is what's being used under the cover in scikit-learn when you're doing clustering algorithm. And topics, so just definition, this basically just means are there themes that are in your data, such as restaurants, amenities, activities. So I love history. I love to see where the stuff I'm learning from a technical point of view, where it came from, because people came up with this stuff. People with feelings and thoughts, and so it was pretty cool. As I was putting this talk together, I actually found that the concept of putting text into numbers, this idea, was proposed in the 17th century. So it's pretty cool. That's a long time ago. They didn't. This is just theoretical, but the fact that someone thought, or that Descartes, that they thought, okay, let's try to do this so that we can have the world's languages converted to words, converted to numbers so that we can do machine translation. Now, to move on to something more applied, in the 1920s, a patent was filed for a statistical machine that searched for documents. This is pretty incredible. 1920, it's like almost 100 years ago. So this was the first applicable, can we actually search for stuff using a computer? And then based on this, Vannevar Bush was inspired by that patent, and after the bombings, he really wanted, instead of knowledge to get destroyed, he really wanted something where all of the world's knowledge could be accessible. And so a lot of the work in NLP really comes from thinking about how can we do machine translation, information retrieval, saving information, being able to access information, and of course, language understanding. So you shall know a word by the company it keeps. This is really the beginning of distributional hypothesis, that words that occur in similar contexts tend to have similar meanings. So what does it mean to have similar meaning? What does it mean to have a similar context? So I just pulled out 2 examples of similarity. There is a very long list. I have the resource in this slide. So the 2 that I'm going to focus on for similar meanings are semantic relatedness and semantic similarity. So semantic relatedness are just any 2 words being related. So car is related to a road, bee is related to honey. Semantic similarity are words that can be used in the same way. So car and auto, that would be a synonym. A doctor and nurse, those aren't synonyms, but you can imagine that in a sentence, those 2 words would be used similarly. So words that occur in similar context tend to have similar meaning. What is context? Is the context a word? Is it a sentence? Is it the whole document? Is it a group of words? So I really wanted you to think about when you're looking at your data, these are all contexts. And it could be that you have very short text. You're going to want to apply different techniques to short text than long text. So you really want to think about, do I want to break up everything as sentences? Do I want to break up everything into 5-word chunks? And based on what your data is, you'll think of context differently. Words that occur in similar contexts tend to have similar meaning. So what does similar context mean mathematically? So the whole point of this is that we want to convert our text into numbers. Do we want to maybe count the words that appear together in a context? Maybe every sentence, you look at the sentence, you're like, okay, I see the word car and I see the word auto, or I see the word car and I see the word road. Sorry for the extra bracket there. Do we want to count how far apart they are? So maybe we want to look at, car and road and see every time, like how far apart they are. Like, oh, okay, in this sentence they're 3 words apart, in this sentence they're 5 words apart. I mean, there's many ways we can decide to count things. I think a lot of you guys are in analytics, so how you decide to count things is very important. So do we want to weight them? Do we want to think of the word car as important as the word the? Maybe not. So because of the different ways we can think about context, similarity, meaning, this is what has led to the evolution of different word embeddings over time. So words. What is a word? So words are printed. They have letters. They're surrounded by white space. Sometimes they're at the end of a sentence, so there's punctuation. Words are combined to form sentences that follow language rules. What is a sentence? Now, this is super easy. I mean, sentences, that's couldn't be easier. You just separate text by periods, exclamations, question marks, and then we have sentences. We just throw that in the computer, and we're good to go. Now, I'm bringing up some of these things because these are the things you're going to have to think about as you take your text and decide to break it up. And so if you decide, I want to look at every sentence and say, okay, this is how we're going to determine sentences. It ends with a period. This would be totally nonsensical. What, 1, 2, 3, 4 sentences? So I'm going to spend a little bit of time in data preprocessing because I think this is very important. This is going to, I don't want to say make or break your analysis, but the way you choose to process your data is going to completely change your results. So tokenize, this just means to split your text into tokens. This is required for GenSim. Scikit-learn has other ways of tokenizing it. You just tell it how to tokenize, but for GenSim, you do need to tokenize. You have to decide, do you want to keep or not keep a bunch of things, such as numbers? Do you want to keep punctuation, stop words. So stop words is actually a list of words that are thought of as not very important in a given language. So again, this is language specific. There is unfortunately no universal list. So scikit-learn has its own built-in stop word list. GenSim has its own built-in stop word list. I am using stop words in the examples I show you at the end, but I usually try to not use stop words. I'd rather have the data tell me for itself what is a stop word and what isn't. So for example, in GenSim, I found out that the word computer is a stop word. Like, I don't know that computer should be a stop word. Maybe like he or it, but computer, it's like, maybe I want to look at data and know, is it talking about, you know, technology or animals? And computer, I don't think should be a stop word. So just make sure that if you're using a package with a built-in stop word list, just look at the list and see what words are in there. Sparse words. You might choose to keep sparse words. You might choose to filter them out. Again, based on how you're looking at your data, you really want to know what it is that you're trying to figure out. If you're trying to figure out very high-level things, you're like, it's okay that people aren't using this word a lot. If you're trying to find some rare occurrence, then you do want to keep sparse words. For those of you doing web scraping, you will want to remove HTML tags. And GenSim, again, has built-in functionality for each of these. So if you're working with web data, you can remove HTML tags that way. And just remember that this is very language specific. So English, great, you have all your decisions of how you're going to apply this to your data. As soon as you have another language, you really have to think about how they use punctuation and how they use stop words, etc. I made her duck. Just wanted you guys to think about that. Think about if there's any ambiguity in how you would interpret that. How many ways can we interpret this sentence? Is there? What? Yeah. Is there more than one way to interpret this? So, cute duck for dinner. Or getting chucked at the head. But they ducked, so it's okay. So sometimes with your data, you will want to annotate. And annotating means figuring out if a certain word is a noun or a verb. Another way of annotating your data is named entity recognition. I had an example here, but I threw it in the back. So I had, I love Apple, or I love my apple, and that can be referring to my Apple computer, or it could be referring to a fruit. So you can choose to append the parts of speech to the data, or you could decide to ignore certain types of parts of speech or certain types of named entity recognition. I'm not going to go into Spacy, but Spacy is the tool to use to do the annotation. It is excellent. It is commercial grade. It's super fast. Spacy it's the way to go. If you're not using Spark, I would say Spacy is the way to go with text. Yes?
And you might be getting to this, but when you're processing the data, can you annotate the data to determine point of view? So, for example, if you're looking for somebody who's worried or concerned, is the person who's typing it worried or concerned, or are they talking about somebody else being worried or concerned? And so having that point of view is important.
Like the context. Let me think about that.
Okay.
And I'll get back. If I can't in here, then I'll get back to you after. I'm trying to think if I've run into that in my work, but
I can give you a more elaborate example.
Okay, that'll be great. So another thing in data processing, pre-processing, is to reduce your words. So one way to reduce words is stemming. You're basically taking a word and reducing it to its word stem. Now, it's a heuristic. You just chop off the word ending. It's really fast. There are many ways of doing stemming. One of the built-in ones in GenSim is called Porter stemming. You can read more about stemming. So basically, it'll turn a word like running into run. It just chops off the ing at the end. Now, another way is to lemmatize. Now, lemmatize properly reduces the word to its part of speech annotation, based on its part of speech. This is available in Gensim. It is slow, but it changes words like better to good. Now, both of these are to your discretion. You don't have to use either of these. Again, think about your data. Is it people just handwriting, whatever, and you want some of the maybe errors in spelling to get cut off, then stemming might be a good idea. Just think about your data and think about, do I want to do this or not? And then look into some of the different stemming options. Another package that I'm not talking about is NLTK. It is slower, but they do have a lot of different stemming approaches. So if you want a different one, you can use NLTK. And then again, remember that both of these are language specific. So just a quick pre-processing example, taking words, the quick brown dog jumps over the lazy dog. We remove stop words, so we remove the, we remove ever, we remove the again. We convert jump, jumps to jump. So let's actually get into some of the word embeddings. So we mentioned before, words can become embeddings, context can become embeddings. So using the example before, this is like the easiest embedding you can have. I won't go into too much detail. This is available in scikit-learn. It basically takes every word. It's called one-hot encoding because every word is given a 1 for its location in the vector and then a 0 everywhere else. And I made this at like 1 in the morning, so I didn't have the column headings, but I'll flip to the next one. So Boolean embeddings. This is just if the word exists, you give it a 1. If the word doesn't exist, you give it a 0. So you see here, all of the words exist because I just have one sentence. But imagine if I had, 30 different sentences and I had a row for each sentence. You can imagine that we would have a much wider data set because it's all of the words, and then you would see 0s and 1s in there. Bag of words. This is basically term frequency. We're counting how many times we see a term. So this is count vectorizer in scikit-learn. We see the word dog twice. I think that's why they changed the sentence, so they could do this example. Oh, I have credits on other slides. Any picture that I take, that I borrow from the internet, I make sure to have the credits. So again, this is a little bit of just terminology, but a document term matrix is taking the example that we saw before where it was just, imagine that sentence was one document. So now we have many documents, we have many terms, and this is what a sort of complete document term matrix would look like. You would expect there would be a lot of 0s because not every word is in every single document. And we have a document vector, we have word vector. Both of those can be considered word embeddings. Let's talk about weighting. So why would we want to weight words? I think I mentioned this a little bit before. It's like if we see the word car in a document versus the word the, I think car is more important. So words like the and the things that we talked about as being stop words, those would be things that we would want to weight. Now, I'm not going to go into the math here, but there is a weighting approach called term frequency inverse document frequency. It's called TFIDF for short. So in the literature, TFIDF, when you see that, it's basically saying, let's reduce the weight of the very common words. And the way that it identifies common words is that it sees that word in many of the documents. So words like the and, you would expect every document to have that. So if every document has it, it's not really that important. And it applies to that document term matrix, the one that we saw on the previous slide. You can't apply this weighting if you just have one document, because then you don't know, does every document have this word? Is it important? So just at a high level, the TF-IDF values are on the bottom. So the things that occur all the time, the stop words, they're going to have a very low TF-IDF value. And the rare words are going to have a very high TF-IDF value. So just to get a sense of if you don't actually want to remove your stop words, just use the TF-IDF. So word co-occurrence matrix. A word-word, this is basically a word-word matrix for a given context window. So I wanted to just show an example of a word co-occurrence matrix. So before we talked about a document term matrix where we had documents and terms. Here we'll have sentences or documents. And we actually take all of the words and then just line them up, rows and columns. And we look at a context window. A context window is basically how many words around it, and then we do a count. So I just highlighted one there so we can just go through that example together. So context window size being 1 means we're just looking at one word to the right, one word to the left, anytime we see that word. So I have like highlighted. So where do we see like? We have I like NLP, I like deep learning. So like is surrounded by I twice. It's surrounded by NLP once and deep once. And so that is how we create the co-occurrence matrix. Does anyone have questions on this? I want to make sure everyone kind of sees that, gets it. Okay. So I'll gloss over this one, but there's also weighting that can be done based on the word co-occurrence matrix, and it's called point-wise mutual information. So there's a higher weight for common words that are infrequent. And so I'll just go to an example because I think it'll highlight it better. So car and driver, they show up a lot together, but they don't show up as much as it and the. So this matrix is basically looking at anytime two words show up a lot, but not so much that it's not really that meaningful. So very similar to TFIDF, but here it's just based on words. And remember, context is important. Instead of just a one window context, you might want to have a 5 window, which I think could address the situation, the case that you brought up. The larger the window size, the better understanding you have of the words in a larger context. So I'm going to really gloss over topic embeddings. So before we were talking about word embeddings. Now there's another layer called topic embeddings, which is a latent space. A latent space basically means it's a hidden space. So there's stuff sort of underneath. One way to do topic modeling, topic embedding, is latent semantic analysis. And for those of you who took linear algebra or love linear algebra, I love linear algebra, I love matrix decompositions, but SVD is a way to, is one matrix decomposition method. And if you apply this on a matrix, it could be the co-occurrence, it can be the document term, or the TFIDF matrix, you'll actually be able to pull out the topics that are in your data set. Now, this is a one-liner in scikit-learn. It is called, I think it's called LSI or SVD, but it's a one-liner to basically pull out these 3 matrices. And what these matrices give you, if you see U, it says words and topics. That's basically saying, if you say, hey, find me 10 topics, it'll tell you the words and how much each of those words plays into each of those 10 topics. Now, for topic embedding, you do have to look at the topics and sort of determine